Hi, welcome to this lesson on calculus. What is the derivative? So let's have a look at differentiation using first principles. Why did we need limits in the first place, as we've seen previously? Well, differential calculus is the field of mathematics that is the most often used in application-based questions in the real world. So how do we do differential calculus? Well, we need to define what a derivative is, and in order to define what a derivative is, we need the concept of a limit. Therefore, that's why we needed limits. So, for example, from modeling the temperature to determining the stock market trends, calculus is implemented as it is the branch of maths that deals with examining the rate of change of objects in relation to each other. So that's extremely important. That's what differential calculus deals with. Derivatives deal with rates of change. So in the real world, whenever we want to research how objects behave, we need to model them with the use of an appropriate function that'll explain the behavior to a certain degree of accuracy. Once we have that function, we would like to know how the objects behave at a specific point in time of that function. So to do this, we would need to find what we call the instantaneous rate of change of the function at that exact point. But what does this mean? Well, simply put, if we have some function and want to know how it changes over time, we want to examine how the gradient of the tangent line. So these are the key words here. So if we examine how the gradient of the tangent line to that function behaves at each point in a given interval, then mathematically we can visualize this process as follows. So imagine you have some function here. In this case, it's a hyperbolic function, f of x equals 1 over x, for example. Now, if we take 2 points, let's call this first point A. It has an x coordinate of x and a y coordinate of f evaluated at x. Okay, and then similarly, what we'll do is we'll add a small incremental amount, which we'll call h. So h is some very small minor amount that we're adding on here, x plus h. Then the x coordinate is x plus h, and the y coordinate is f of x plus h. Okay, so now, if you look at this line that goes between those 2 points, there is an average gradient. And the average gradient between those 2 points is essentially the gradient of the straight line between the 2 points. So for example, if this is x1 and y1, and this is x2 and y2, we know the average gradient is y2 minus y1 over x2 minus x1. All right, so that'll give us f of x plus h, that's what y2 is, minus f of x, which is y1, all over x2 now is x plus h, and x1 is just x. So in the numerator, we have f of x plus h, which is the y value of the b coordinate, minus f of x, which is the y value of the a coordinate, all divided by, well, the x's will cancel here and we're just left with h. So there's a formula which we call the average gradient of the function between 2 points here. Now, what happens if we let h go towards 0? So that means that this value is going to keep getting smaller. And can you see now that a straight line, so all these points here I'm plotting, so h is getting smaller. So we're going to keep looking at all those lines that go through that point and that intersect through A. So as you let h go towards 0, what will end up happening in the long term is we'll just be left with one tangent line at that point that only touches A. Therefore, it's a tangent line. So essentially, like we said, yeah, the average gradient between the 2 points is given by this formula. And the derivative, the first derivative at the point A, is defined by taking the limit as h goes towards 0 of this expression here, of the average gradient. And then that'll give us that singular tangent line, which has the formula y equals mx plus c. And the gradient of that tangent line, is equal to the first derivative. And the notation we use is f prime of x at that point. Okay, other notations that we can use for derivatives. So for example, if you have y equals f of x, Then f prime x, that is the first derivative of the function f with respect to x. We can write it as dy by dx. That means the derivative of y with respect to x. So this notation here, this sort of fractional notation, is thanks to the mathematician Leibniz, and f prime x as well is another notation accredited to him. Sir Isaac Newton, a very famous physicist and mathematician as well, is also accredited in around the same time period on working on calculus, just like Leibniz was. So they came up with very similar looking notations. For example, Isaac Newton's notation for the first derivative was x dot on the top there. Okay, so these are all different ways we can write the derivative, but the two most common ways are f prime x and dy by dx. Right, you can also say capital D subscript x of the function f of x, right, and so on. So there's a few notations, but the most commonly used are these two here, f prime of x or dy by dx, the derivative of y with respect to x. Okay, so that is what the derivative is. The first derivative, f prime x, is defined as the limit as h goes towards 0, or h tends to 0, of this entire expression. So algebraically, once we know a function, we will work out this entire average gradient expression, and then at the end, evaluate the limit, as we've seen. Right. Okay, so that is deriving from first principles. Let's go ahead and practice some questions with it. I'll see you in the next one.